Hi, I'm Stacey and welcome to my YouTube channel. In this video, I'm going to be going over my favorite state machine. That might sound like a pretty funny thing to say, like, Stacey, why do you have a favorite state machine? What's so special about it? This state machine has evolved over several years. As I've kind of gone along, I've kind of tweaked it to the way that I like it. And I'm going to be sharing it with you today. I'm going to be talking about how it works, why I like it, and how you can use it. So, the states don't actually matter. You can put in whatever states you need, whatever states make sense for the project. I use this state machine in pretty much anywhere I need a state machine, and also, which is a lot of my modules. So I'm going to go through this example quickly. This is a very simple example of a state machine. Basically, we're in the idle state. If the valid goes high, we enter the start state. And then after the start state, we go into the data state. And then after the data state, we go into the stop state, and then wait, and then idle again. So it's a very small, simple state machine. It's just an example. I like to label my clock cycles. I want to know the kind of clock cycle I'm in. Am I in a start clock cycle? Am I in a data clock cycle? And then that will inform the behavior of the signals in the FPGA. The most simple example of this is a reset. If the FPGA is in reset, then it behaves in a certain way. It will reset all the output signals. When it's not in reset, it does something else. And those are two circuits that are both inside the FPGA, the reset circuit and the not reset circuit. And even when I'm not in reset, the reset circuitry is still there. It's just not being used. And when I'm in reset, the other circuitry is still there. I'm just not using it. And in the same way, I can decide what kind of clock cycle I'm in. And so when I'm in the start clock cycle, then the FPGA is going to behave in a certain way that I'm going to describe. And when I'm in the data clock cycle, the FPGA is going to behave in a different way. And so this way, I can compartmentalize the behavior of the FPGA into different states. And that helps me understand what the code is doing and clearly define what the FPGA is going to do. And that's what this is about. It's a hardware description. So we are describing the behavior. And this way we can compartmentalize the behavior. So during the start state, I only have to worry about what I'm going to do during the start state. For the data state, I only have to worry about the data state. And so I have this ability to compartmentalize the behavior. And that really helps in really complex designs. So in this always block, this is a combinational always block, which means that this signal's value is determined immediately. So the moment the valid signal goes high, I go into the start state. If I'm in the idle state and the valid signal goes high, I immediately go into the start state. I am not waiting for the next clock edge. And this is really useful so that I can immediately decide what I'm going to do next. I kind of see this always block as a little bit of an island. And this is the next state island. So in this island, I am determining what the next state is going to do, the behavior of the next state signal. And so I like to keep the island just for next state. So I don't put any other signals in my little island, only next state. This is my chance. This is my opportunity to describe the behavior of next state. That's it. That's all I get. I get that always block. I can't go and put next state on the left-hand side anywhere else, just in this always block. And I find that just keeping the always block limited to the next state signal, it allows me to easily and succinctly see the behavior of next state. So this waveform is described like this. And this is how I work. I kind of see in my head the waveform that I want, and then I try and write the code to describe that waveform. So I will write the code, do a simulation, see the waveform, and then tweak it like, oh, I need it to be like this. Just like in programming, you write the code, you look at the output. It's an iterative process. The same with FPGA design. I write a code and then I look at the waveform and I tweak it and I look at the waveform. And so that's why often I will supply the waveform with the code. because that's our natural feedback loop for development. So this waveform is produced by this code in the current state that I'm in. If I'm in idle and the valid is high, then I go into the next state is start. And in start, the next state immediately goes to data. And if my state counter is 7, so I've been in the data state for 7 clock cycles, then I stop, and then I wait, and then I idle. And this is a really nice little summary. It's all condensed into one little spot. And that's the first thing I like about the state machine. It's very clear to see the behavior of the state machine. And so here's the next part of my state machine, my next island. This island, and this is a combinational always block. If you look at my FPGA basics videos, I go over the difference between combinational and registered logic, or synchronous and asynchronous logic. And this is a combinational always block, which means it is not registered, which means that the output, the signal, is driven immediately. Immediately next state will go high. And this is very useful if you want an immediate response to an input. I do not have to wait until the next clock cycle before I start responding to my input. And that's really useful. When the valid goes high, I immediately know that I'm transitioning into the next state. Then we register the next state into the current. So this is deciding beforehand. I am preparing. I am prepping beforehand, evaluating my conditions, and then saying, okay, now I am going into the current state. So I am switching states. I'm deciding beforehand, which is the next state, and then this is me actually going into that state. And you can see here that there is this clock cycle delay between the next state and the current state. And so here I know that I'm preparing to go into the state, and then current state is when I'm in the state. You can see that there's this 1 clock cycle delay between the valid and the start. So if we didn't have this next state, then we would only know that the valid had gone high and that we were in the start state here, 1 clock cycle later. So there's a bit more of a latency if you don't have the next state signal, which is the second reason why I like the state machine. I have access to the next state signal. It allows me to know what state I'm going into immediately. Okay, the last piece of my state machine is the counter. And so this is the way that I keep track of how long I have been in a state, is the state counter. And so in this case, state counter is 7. So that means I remain in the data state for 8 clock cycles because I start counting from 0. So it's for 0 through to 7. And this is the code that produces that counter. And what's nice about this is that it's automatically going to be counting however long I'm in a given state. So I do not need to reset the counter. I'm automatically resetting the counter when the state transition occurs, which is when current state is not equal to next state. I am automatically resetting the counter. I don't have to worry about manually resetting it anyway. It's just always going to reset. And as long as the state counter is appropriately sized for your conditions, so if I want to say state counter equals 100, I need to make sure that my state counter signal is big enough to hold the number 100. Otherwise, it's going to overflow and not work. So that's the only thing you really need to be aware of with the state counter, is making sure that it will be big enough to hold your biggest signal that you need, or your biggest condition. And so this is basically everything. This is the 3 parts, the 3 islands that make up my favorite state machine. We have the next state definition, we have registering the next state into the current state, and we have the resetting of the state counter. So you say, okay, Stacey, but how do I use this? Like, how is this useful? How do I actually do anything with this? Like, okay, yay, we're labeling our signals, but now what? Okay, well, let's give an example. So here we go. So this is how I would produce an output signal based on the values of my state machine. So I can have a case statement for every single state, and then I just drive my output signal according to the values that I want. So during the idle state, it has the idle value. So this is just a constant defined. So in this case, it's 0. The start state, it's 1. The data state, it's the data out. The stop state, it's the stop value. And the wait state is the idle value again. And so here, very succinctly and clearly, I can define the way that my output signal is going to behave. And this is really useful. This is its own little island that I can use to define my signal. What's interesting is that this code is less code than this code. So I spent all of this time setting up this framework, and then the actual definition of this output signal is actually quite simple. So I set up my framework, but then the actual output code is actually quite small. And this I see quite often, where the majority of the time you are actually defining the framework. I kind of see this as a framework. This is my framework. And then I tie my output signal's behavior to that framework. So we have a conditional framework, and then we tie the behavior to the framework. And you say to me, but Stacey, why do I need to tie my conditional signals to the framework? Like, why can't I just use this valid as the start? And when the valid goes high, then I'm like, oh, okay, cool. The output must be idle. Why do I need to have all this state machine business in between? Let me give you an example. Say, for example, my transition from idle to start was not just triggered by valid. Say, for example, it was triggered by an axis stream, 4 signals: ready, valid, lost. Okay, 3. Ready, valid, lost. So now in here, instead of just having valid, I have a string of, 3 different signals that I need to check: ready, valid, lost. If I didn't have the state machine and I didn't have the state machine on this output, I would also need to have ready, valid, lost to drive this output case. So I would have ready, valid, lost in multiple places. I might have it in multiple parts of the code. I'd say, oh wait, the start trigger, ready, valid, lost, might be here and there and there. And so it might be here, and then it might be here. And so then now I have 2 places. So say, for example, I want to add an enable. And so I go here and I say, okay, I need to change this ready, valid, start, enable. But then I also have to go to this point and change ready, valid, start, enable. And so if you're not tying your output signal to your framework, to your state machine, anytime you change one thing, you have to go change it in all the different places. Whereas in the state machine, I can change it here, ready, valid, last, enable. I can put whatever I want there. And then when I use the start case, I never have to think about it again. I just, I'm in the start case, I'm going to behave like this. And so it reduces code duplication because you're only defining that event once. And that's what I like. I kind of see this as an event-based design where I am defining my state change based on an event. And when I put that event into the state machine, the goal is to only have to worry about it once. And so if you are triggering the behavior of multiple signals on one event, then being able to put that one event into the state machine, and then everything else follows. It all just falls out and naturally follows. And so if I change the framework for that event, and I put that event into the framework, and I change it in the framework, all of the other things just naturally follow. And I don't have to worry about going to 3 or 4 places in the code because that event changed, and now I have to go and change the signals. And so from a code simplicity point of view, this is really useful. I also find that this is how I think, and I like to code the way I'm thinking about it. So when I'm coding the state machine, I am thinking about the state transitions. I'm thinking about the conditions that will cause the state to change. And so that's clear. It's clear here. If it's valid, then the next state is start. That's very clear. When I am deciding the output signal's behavior, I'm not necessarily thinking about the specific signals. I just want to think about the start of the packet. So I can just say, at the packet start, this behavior occurs. And so that's abstracted away. My brain doesn't have to go through the hoops of, oh, the start is ready, valid, enable. Therefore, in order to change this output, I need to do ready, valid, enable. I don't have to jump through those hoops. Now here, start, output is this. Data, output is this. I don't have to think about what start means here. I can just define it. Start, signal, behavior. Whereas, and yeah, I just have to think about the state transitions. I am intentionally separating the framework from the output behaviors. And that's really useful when designs get big and you have complex signals that you need to describe. So one of the other nice features of the state machine is being able to detect state transitions, because it's not just about the output data during a state. So for example, all of these are defined by what state I'm in, right? I'm in the data state, I drive data out. When I start state, I drive start out. It's easy. One of the other important events that you need to know about and consider is the state transition. So a very simple example is when I'm going from the start state into the data state. Often you'll be reading data from a FIFO, from other source. So if I know when I'm going into the data state, then I can preload my data. So the cycle before I'm going into the data state, that is when I'm reading from the FIFO. I am loading up my data buffer so that I can start prepping for it to be driven out during the data state. If you only have one state signal, you don't know when you're going into the data state until you're in it. It's only when you're in the data state that you know, oh, I'm in the data state, I need to start preloading. Whereas at this point I'm in the start, and it says the next state is going to be the data state. This is the point where I can start reloading my buffer. So I can detect a state transition. And that means that when my current state is start and my next state is data, that's when I pop data off the FIFO. And that's when I load my buffer in. And so by the time the state transition occurs and I head into data state in the next cycle, it's all there. And that is really useful. So for example, here we can detect a specific state transition if next state is start and current state is idle. So that way you can prep your signal values going into a state or any state transition. This is an example of my state machine counter, the state counter. It will literally reset on any transition. And I can go from one state into any other state. So for example, if I'm in the idle state and I need to detect any other state, so I'm going from the idle into any other state, or I'm going from a specific state into any other state. This is useful for handling error conditions. So for example, if you detect an error and you want to go into an error state, you don't necessarily care where you came from. You can just say from any state into the error state, I am doing something. And so you don't have to duplicate that code for from data into error, from idle into error, from blah into error. You just have anything into error, and you have one set of code that handles that event. But you still know where you come from because you still have current state. So if your next state is error and your current state is idle, then you can record that and you can say, yes, I went from idle into error. And you can log that somewhere or trigger, drive a signal with that value. But you do not have to write code for every single combination of something and error. You can trigger an action based on a flag, or you can stay in your state for as many clock cycles as you need. You can refer to any clock cycle within a state. So for example, if I want the fifth cycle of the data state, I can do that. And all of this is within 29 lines of code. And this is the thing, is that it is such a flexible way of defining a framework and being able to define the way that signals are going to behave in a very succinct, easy to understand, and easy to come back to later. If I go away and I come back to this code, I can easily see the way that the state machine is going to operate. And I can easily see the way that the next state is going to be defined. I just also want to point out that I always put this next state as current state at the top of the combination always block so that I don't have to worry about inferring a latch. My FPGA basics video has what a latch is as well and how to avoid them. So let me show you some example code. This is an example that I've put together of a state machine that has the traditional single always block style. As you can see, there are a bunch of signals that are defined in the always block in addition to the state signal. And the thing with this is that then it'll be very difficult when you go through, say for example, if I haven't looked at this code in a year and I come back to this code and I'm trying to refresh my memory of how it works, I have to dig through this always block to look at these states, to see these state transitions. And it just makes it a bit more difficult and a bit less clear to see the way that the state machine is going to behave, because you have all of these additional signal defines that are included in the state machine. And you can see here, I have to kind of go through and look for all the state transitions at the bottom to be able to see exactly how the state machines are going to behave. And so that just makes it less clear, especially these, you've got all of this other stuff that's included here that we don't really need in order to be able to tell how the state machine is going to behave. This doesn't have a next state and a current state. This just has a single state. And that means that if you want to do something in that state transition, the only place you can do it is here. If I wanted to do something in the state transition and I wanted to know when I was going into state from state 6 into state 1, the only place I would know is here. And so if I wanted to drive a signal during that transition, I would have to include it in the state machine here, because that's the only time I know about it. And this is the problem with only having a one state signal, is that then the only time you know about the state transition is in the state machine always block itself when you go from the one state into the next. This is the only place where you can do it. But by having a next state and a current state, I am able to separate out my state machine into multiple little islands that I love. That's the way I love to do it. And that's why I love the state machine, is because it allows me the flexibility of being able to write clear, concise code. So what would I do if I was presented with a state machine like this? The first thing that I would do is copy and paste it. So you take the entire state machine like this, just select the whole thing, and I'm going to copy and paste it like this. There we go. Control C, Control V. So now I have a duplicate. So I'm going to go back to the top. There we go. And the first step is I'm just going to take out all of these other signals. All gone. So the only thing that's on the left-hand side is the state. Where's my state? I don't even see it here. There it is. Okay. So immediately, there we go. So that is already a lot better. So now I just have my state signal and I can just see the state transitions. If this, then we go there. If this, then we go there. Immediately, much, much better. And then we go to my second copy. And now now I'm going to take the states out, right? So I'm just going to go through here, and every time, because remember, a signal can only be driven on one island. I can't have the signal on the left-hand side in more than one island. So if I have the signal on the left-hand side on the state always block, I can't have that signal on the left-hand side here as well. That will cause a conflict. So I'm just going to take all of these state ones out. And so then this becomes the always block that defines the behavior of all these other signals. And this is a matter of style. You could separate this out even further. You could say, oh, okay, signals 1 to 4 go into their own always block. And I like to kind of structure that, where I like lots of little always blocks, and they are related signals. So there might be delayed versions of the same signal, or they might on the same island, or there might be all of the same bus, like an AXI bus or AXI stream bus. All the signals are related, or all the signals that are valid at the same time on the same clock cycle, those ones. So all the signals that are in sync on the same clock cycle, in alignment, those will go on the same island. So I kind of like to structure my islands where an island doesn't have more than, say, 10 signals. And so what I would do with this, even to make it even more clear, is I would copy and paste this again. So now this doesn't have any state signals in it. It just has all the extra bits and pieces. And I would copy and paste this again, and I would go through and say, oh, okay, I only want these 10 signals because these are related. And then I'd go through and individually isolate out. That's what I would do if I were refactoring code that was like this to make it more readable. But that's a matter of style. Some people would prefer to have one big always block, and that's up to them. But I highly recommend separating out your state machine and having an external current if you want to make your code more clearer. I personally think that it's more clearer, but other people might not agree with me, and that's okay. Okay, so this is my Ethernet packet generator, and again we see the state machine. I create the next state according to whatever conditions I want to change state. So in this case, there's enough data in the FIFO, then I change state. I think I have a video going over the contents of this file already. And then this is the example of how I drive the output data based on those state values. So when I'm in idle, then the state values are these values, and then preamble, the state values are these values. And so again, I'm tying the output signal values to the state machine. And this way I can create little islands. So for example, this island has 4 signals on it, and I basically go through every single state and I decide the value of each output depending on the state. And it's very clear what values the signals are going to have in each state. And the goal is to keep the islands relatively small so that you can clearly see at a glance how the signal is going to behave in each state. Here's an example of how I use the state transitions. So for this is the frame check sequence. So when I'm going into the frame check sequence state and I'm not in it already, so this is the state transition into the frame check sequence state from anywhere else, then I load up the frame check sequence into the frame check sequence buffer, because I know that I'm going into the frame check sequence state, and so I'm going to be needing that data. And the same going into the data state and knowing that I'm going to need the FIFO data into the data buffer. So then I will drive the FIFO data into the data buffer and I will pop that off the FIFO, which is what this FIFO read enable is doing. So this way I am loading in based on the state transition. So this is the state machine paper that was written by Cummings, and he actually describes the state machine style. It is the 3 or 4 process state machine style. It just depends. It's this one, the 3 block and the 4 block. This particular technique is pretty well documented in this paper, and it's actually a really interesting read. Let me just head down to that sections. So it describes how these state machines can be designed, and it goes into the details of the way that they are synthesized, and it has tips and tricks as well on how to write more efficient state machines. So if you want to up your state machine game, this is a really, really good paper to go through. It is extremely detailed. It even goes through coding techniques and style requirements that they use a different style from me. I don't exactly follow the style that they recommend, but I've kind of tweaked my own state machine over the years. But this is also the study of how much space the state machines take up, how they're synthesized, the efficiency of how they're synthesized. So it is a very, very interesting read if you would like to get into more detail on this kind of state machine and how state machines are described in hardware description languages in general, and how these tools synthesize these state machines. So that's it. Thank you so much for watching my video. I hope it was useful, and I will put the code in the description. It's so short, I can just put it in the description. So that's what I'm going to do. Thank you very much, and I'll see you next time.